Limits are a fundamental idea of calculus. Everything that we will go do from this point on will have some sort of reference back to the idea of limits. The main focus that we're going to be dealing with in regards to the middle part of this course deals with the idea of derivatives. The idea of derivatives come from the idea of limits. We utilize limits to be able to calculate the idea of derivatives. When you're looking at a limit as a value from the domain is approached. The value from the range approaches a value. This is called the limit. So as you basically have two moving objects here on a graph, x is going to get closer to a value. What is y getting closer to with respect to our function then? As x gets closer to a value, what does y get closer to? And that's, once again, what you can mentally put into your brain. As x gets closer to a value, what does y get closer to? As your domain gets closer to something, what does your range get closer to? And that's how you can sort of, remember, that's how I dummy it down for my brain. Okay, I dummy it down to my brain. As x gets closer to a value, what does y get closer to? So you have two moving aspects here. X is just getting closer to a value, but you're looking at a function. What does y get closer to looking at this function? F of x equals x squared. What does f of x get closer to as x gets closer to a value of 1? Well, let's take a look at this. X is getting closer to a value 1. How we can write this, how we write this idea is we use the LIM, which tells you have a limit. What does f of x get closer to as x gets closer to a value of 1? So underneath this, we get our x variable, and we get our little arrow in here. This tells us a limit as x gets closer to 1, or as x approaches a value of 1. So this is our limit as x approaches a value of 1 of a function which is f of x, or we could write this a limit as x approaches 1 of x plus 2. So we take the limit of a function, of a rule, of an equation, and we tell, basically, okay, the limit as x approaches a value of 1, x is getting closer to a value of 1. We're getting closer to a value of 1. We don't say we're equaling a value of 1. We just said we're getting closer to a value of 1. So when you think about the idea of a number line, we have 0, 1, 2. What we are doing is we are getting closer to this value of 1. But we're never quite achieving it. So it's like having an open dot there at the value of 1. We are getting closer to this value of 1, but we're never achieving. That's the idea of an open dot. When we were graphing our inequalities, when we were graphing those inequalities, we put when we just have less than or greater than, we put an open dot there because we're never equal to. But what we always talked about, we get closer and closer to the value of 1, but we never equal it. That's why we have an open dot there. Okay, so if we take a look at this, is just a basic fundamental idea of limits, how we draw limits and what we think of, or how we write the limits. We have how we write it, and this is sort of the theory behind this. But what we're looking for as x gets closer to this value of 1, what does our y value get closer to? What does x plus 2 get closer to? Well, let's take a look at some ideas here. We're going to look at a function limit x approaches 1 of 5x minus 3. So we're going to get closer to the value of 1. So we're going to look at this as an idea of a function. Okay, if I have 0.5, then I go 0.75, then I have a 0.9 and a 0.99. These are our x values. These are the x values. And we're signifying we're getting closer to the value of 1. We got 0.5, 0.75, 0.9, 0.99. And what we're wanting to do is we want to evaluate this function. We want to see where this function lands at. So we can plug into our function the value of 0.5, the value of 0.7, value of 0.9, value of 0.99. So we have 5 times 0.5 minus 3, 5 times 0.75 minus 3, 5.9, 5 times 0.9 minus 3, 5.99 minus 3. Jack, what do you get for our values over here?
-0.5, 0.75.
So if I put 5, okay, you get 0.75 here for the second one?
Yeah.
Next one?
1.5 and 1.95.
We good with that? Okay. So if we take a look what's occurring here, let's do another value. Let's go our function value of 0.999. What is our function value of 0.99? 0.999. 1.995. What is our y value getting closer to as we get closer and closer and closer to the value of 1?
It's getting closer to 2.
We're getting closer to 2. We got negative 0.5, then we go 0.75, then we go 1.5, 1.95, 1.995. So we are getting closer to the value of 2. Getting closer to the value 2. We're never quite achieving it, but if we take a look once again at a number line, x is an open dot and a value of 1, we're getting closer to that value of 1. But we're never quite achieving. What is y getting closer to as x gets closer to 1? Go ahead and do the second one. Todd, did you read down your values? What do you get?
2, 1.5, 1.2, 1.02.
So as we look at this, we go from 2 to 1.5 to 1.2, 1.02, 1.002. What are we getting closer to? Mike? We're getting closer to a value of 1. Let's go back up to this one up here. Limit as x approaches 1 of x plus 2. So we have f at 0.5, f at 0.75, f at 0.9, f at 0.99. We're adding 2 to this, so hopefully we don't have to clickety-clack through our calculator. We have 2 plus 0.5, 2 plus 0.75, 2 plus 0.9, 2 plus 0.99. And the value that we get closer to here, if I go 2.999, that would be, I'm sorry, 1.999, that would be 2.99. The value we get closer to here is a value of 3. So if we look at what's happening here, limit as x approaches 1, 5x minus 3 came down to 2. Limit as x approaches 1 of x plus 2, we came down to value 3. Limit as x approaches 2 of 5x minus 2, we came down to a value of 1. What is occurring here? What could we do with respect to being able to evaluate a limit?
Just plug in the limit for x.
If we put in the value of 1 in for x, we have 5 minus 3, or 5 minus 3, which is a value of 2. We have 5 minus 2 times 2, which is a value of 1. And if you think about our graphs, if we look at x plus 2, if we look at x plus 2, the graph of x plus 2, we have a y-intercept of 2, we have a slope of 1. What we're looking at with respect to our graph, we are saying our x value is getting closer to 2. So here's my x value, I get this y value. This x value goes to this y value. This x value goes to this y value. We are just climbing the ladder in regards to our line, and just working ourselves up this line here. As we go up this line, as x is a value of 1, what are we approaching here with respect to the value of 1? Well, we're approaching the value of 3. So basically, we're just plugging in the value. Well, you might sit there and say, well, what's the sense of having limits then? Well, there's other facets of limits, but we first need to understand what is the idea of a limit. How can we solve limits? The first method we have of solving limits is just the substitution principle. The limit of x approaches a of f of x is just equal to f of a. And that's the first thing we want to do when we're trying to find limits. That's the first thing we do. We just plug it in. Plug it in, plug it in. Okay, we just plug it in. But there's other facets of limits that we will have to deal with that will not allow us to do this. We have to go back and take a look once again at discontinuities, okay, or look at what is called a discontinuity. A discontinuity is a value from the domain that makes the function undefined. A discontinuity is a value from the domain that makes the function undefined. It is basically it is your exclusion value when you're stating the domain. What's your exclusion value? What can x not equal? Because it can't equal this because it makes us undefined. These are the ideas of discontinuities. Well, if I take a look at my first function here, f of x equals x plus 3 over x plus 4, what would be our discontinuity? What makes our function undefined here? Sure. -4. X equals -4. What would our discontinuity be over here in the second one? What makes our function undefined, which makes it basically, what makes our denominator equal to 0? Justin, what do we have for the second one? -6 and 1. Because we can factor that to x plus 6, x minus 1. Signs have to be different, so we don't use the 3 and 2. Okay? Don't use the 3 and 2 in there. So let's take a look at now some other limits. Limit as x approaches 5 of x squared minus 5 over x minus 5. Well, what we just learned on the front side, the first thing that we want to try with respect to limits is just plug it in. Plug it in, plug it in. Well, if I plug in the value of 5 here, we have 5 squared minus 25 over 5 minus 5. Which gives us 0 over 0. Which is an indeterminate form. Houston, we have problems. But we still want to be able to find limits. We still want to find a limit. So if we take a look at the idea of limits, what could we do with our numerator here to maybe help us out? We have x squared minus 25.
Factor it out.
Factor it out. Let's see what happens when we factor. Well, if we factor this, we have the limit. Don't forget to carry your limit along here. We have the limit as x approaches 5 of x plus 5 times x minus 5 over x minus 5. What happens to the x minus 5s? Yeah, they go bye-bye. They cancel out. So what we're left with now, don't forget your limit. Limit as x approaches 5 of x plus 5, which now we can substitute in. With your calculator. In your y1, I want you to type in the quantity x squared minus 25 or divided by quantity x minus 5. Make sure you quantify top and bottom. go to your value function. Go to your value application on your calculator. Calculate your value of 4.75. .9, 4.99, and then 5. Brandon, what do you get? 4.75?
9.75, 9.9, 9.99, and then
You get nothing there. But if I take a look at my graph looks like a line. And it gives you a darn blinking spider every time where you're at. But when you go to the value of 5, there's nothing there to go to. What do you think occurs at that point on your graph? What's there? An open dot. You have an open dot. And this open dot is going to occur at the ordered pair x equals 5 and y equals a value of 10. You get an open dot there. Because you get a blinking spider for each one of these, but when you get to this point, it gives you nothing. So if there's nothing there, you have an open dot. Well, if we take a look, we have a discontinuity. We have a discontinuity at x equals 5. We have a discontinuity there at x equals 5. The process that we just did here is called removing the discontinuity. If I could spell. We removed the discontinuity. And we removed that discontinuity, we're able to calculate a limit. If I try to put 4 in here, I get 16 minus 16. On the bottom, we get 16 minus 12 minus 4. So we get 0 over 0. We have a discontinuity there. So let's take a look at eliminating that discontinuity. Factors x minus 4x plus 4 on top, x minus 4x plus 1 on the bottom. X minus 4's go bye-bye. So we're left with 8 over 5 for our value of the limit, plugging in the value of 4 and 4. So what we would get on a graph, we get an open dot at the ordered pair 4 and 8/5. Some other scenarios we run into, if I try to put 5 in here, I get 8 over 0. There's no discontinuity to remove. We can't factor top and bottom. But as I get closer to the value of 5 here, what happens is my numbers are going to get really, really big. Or really, really small. And I'm going to go towards positive or negative infinity. So our solution is a positive or a negative infinity. Last type of scenario, if I put 0 in here, I get square root of 4, which is 2 minus 2 over 0. We have problems. So I'm rushing through this, but we're sort of close on time here. So what we can do is we can multiply by the conjugate. So I'm going to take the conjugate of my top. So if we look at the conjugate at the top and we multiply this out, square root of h plus 4 times square root of h plus 4, I'm sorry, that should be an h, will give us an h plus 4. We have negative 2 square root of h plus 4, positive 2 square root of h plus 4, they go bye-bye. And then we have minus 4. On the bottom, let's leave it alone. Because what will happen nicely, the 4s will cancel out. So we're left with h over h square root of h plus 4 plus 2. And then what will happen is our h's will cancel out. Now if I try to substitute in, we have 1 over 0 plus 4 square root of 0 plus 4, which is 2. Or square root of 4 plus 2. 0 plus 4, I'm plugging h in for 0, which is 1 over 4. So you have different scenarios that you have to deal with. Removing discontinuity, not removing discontinuity, and then working with a conjugate. Homework on page 102, 103. You have 11 to 31, the odds. We'll work on this more tomorrow. Adios. Have a good day.